I want to talk about equilibrium. And the main reason I want to talk about equilibrium is that I'm losing it, you know, because of robotics and everything. I'm definitely losing my equilibrium. Many of you are going to go on and study engineering, and if you do, these two equations are going to be the basis of a class you're going to take called statics. And it's one of the first really tough engineering classes you'll take. Usually it's a sophomore level class. But the whole thing can be expressed by this. If you sum the forces on an object, if it's in equilibrium, this equals 0. If you sum the torques on an object, if it's in equilibrium, when you add up all the torques, it will be equal to 0. Now, I think, based on what we did in mechanics, we covered this pretty well. But basically, if an object is not accelerating, when you draw a free body diagram of that object, all the forces have to cancel each other out. There's no net force in the x direction, the y direction, or the z direction. It's in equilibrium. That doesn't mean it's not moving, right? An object can be moving and be in equilibrium. It just means that it's moving with constant speed in a constant direction. Okay? It lacks acceleration. So if I have a beam like this, okay, and let's say this beam is pinned to the ground like this, and here's a center of mass like this, and so gravity's pulling it down, and let's say maybe I've got a force, you know, like the force pulling up on it at a certain location, and maybe another force pulling down on it like this, and then of course you've got mg pulling down on it like that. So we'll call this F1, and I'm just kind of making this up as I go along, F2, and so on. Now, here you've got an unknown force. It's pinned there, and so maybe you want to know, okay, what is the force acting on, you know, by this pin, on this beam? And, well, oh, and you know what? Hold on. Just to make it more interesting, just to make it a little bit more interesting, we'll make this at an angle like that. There you go. That's better. Come on, this is AP physics. We gotta make it hard. All right, so so this is F2, and F2 has a certain angle, theta, and so on. Now, one of the things you can do to figure out what this force is that you can, if you say, okay, this object is in equilibrium, and you can say, all right, well, if I sum the forces in the x direction, what does it have to be equal to? 0. And this will, then you look at this and say, well, here's some unknown force due to this pin. And then, you know, you've got, you know, you look at it and you say, all right, well, here's the only force in the x direction. These are all both in the y direction. So, you know, this has to be equal and opposite. So you can use this equation to solve for that force right there. Then you can sum the forces in the y direction, and that'll also be equal to 0. Okay, and now this one's a little bit more complicated because, look, here this one has the component, it's only F2 sine theta, and then this is positive, but these are negative. And so you'll get, like, you know, you say, okay, F1 minus F1 minus mg plus F2 sine theta equals 0. And so this is an equation that will allow, oh, wait, I left something off. What did I leave off? I don't know, let's say, I don't know, it's F3 or something like that, I don't know. And so it'll be plus F3 in the x direction. So this is to find the x component of this. I'm sorry, I am getting really, the y component. I'm being stupid, sorry. The y component. So you just look at all the forces and then you say, okay, when I add all these, you get 0. So this lets me solve for an unknown. But sometimes based on what they give you, maybe you don't, maybe F1 is unknown. Maybe they don't give you F1. Maybe they give you F2, but they don't give you F1. And so you've got an equation with 2 unknowns in it. Well, one thing that students at your level is oftentimes forget about is that if this object is in equilibrium, if it's static, it's not moving at all, or it's moving with constant velocity, but obviously if it's pinned down, it's not moving at all. Let's say this object is not moving at all. Well, then we can say also that no matter where I measure it, if I sum the torques, that's going to be equal to 0. Now, here's the beautiful thing about this. It doesn't matter where you measure the torques from. You can pick any location on this beam to be your pivot point. Because guess what? There is no pivot point here. It's in equilibrium. It's not changing its angular position, right? It's fixed. It's static. So no matter where you measure the torque from, there can't be a net torque on the beam. Because if there was a net torque on the beam, there would be an angular acceleration. So what you do is you pick a pivot point, and let's say you say, well, here's an unknown force, and maybe this is unknown. So here's what you can do. You can pick a place to measure the torque from that eliminates one of the unknowns. And when you do that, that leaves only one unknown in your torque equation, and you can solve for it. So I'll pick the obvious one, is right here. If I make that my pivot point, then all the torques will be measured from here. Now why is that good? Because what is the torque due to this force if that's your location? It's 0, because torque is equal to R cross F. And what is R? It's 0 for this force right here. This is a really important idea. Yeah, and by the way, those of you go on and study engineering, this is going to be drilled into your head. So you heard it here first, okay? Now, well, you would say, well, here's, the torques are, well, let's say R1 and F1. R1, F1. And then we have plus, we'll make this just, maybe we can call that L over 2. L over 2, the length of it, cut it in half. Let's say it's a uniform beam. Okay. And well, let's say this is at the end of the stick. Or you just give it some length. Okay. Well, so we'll just call that R. We'll just call it R. From here to here, we'll just call it R. And RMG. And then from here to here, well, you've got minus, because it's trying to make it rotate this way. Well, these might be negative. Anyway, it's in the opposite direction. And so you would go R2, F2, right? There's the torque, sine theta, right? You need only this component of the force is contributing any torque. And then this all has to be equal to 0. Now, what does this torque equation allow you to do? Well, if F1 if F3 and F1, if those are your 2 unknowns, you've just eliminated F3 from the equation. Now your only unknown is this, and you can solve for it. And once you solve for it, you can put it into this equation and solve for F3. Or some variation of that. Okay, so you'll quite often, here's one thing they'll quite often give you. They'll give you and I don't remember if it's on today's practice test because I didn't have time to look, sorry. But they'll quite often give you pinned stick. We love pinned sticks. So you take a stick, you pin it down, and then it's held by a string. You put a string right here, and maybe they hang a weight on it right here. Okay. So they might ask you, what is the tension in that string? So what is that string doing? Okay, it's keeping it in equilibrium. And so, you also have a center of mass. So you have a force here, and a force like this. And then you have some unknown force on this pin. Well, eliminate it and use torque. You know, you can use this torque to figure out what this force is. Okay? Then what they're going to do is they're going to cut the string. And when they cut the string, what's going to happen to that stick? You're going to have an angular acceleration, and then it's no longer in equilibrium. Then you say, okay, the net torque, am I still on screen? The net torque is going to be equal to I alpha. Then you got to figure out what I is at the end of this stick, and then you have to figure out what the net torque is, and you can solve for alpha or something like that. But this idea of equilibrium is both in terms of force and torque is a really powerful problem-solving tool. And if you're a civil engineer, and I hope some of you go into civil engineering. Civil engineering sounds kind of boring to some people, but I'm telling you, it's the civil engineers that allow civilization to take place. And so if you're going to design a bridge, or maybe an architectural engineer, you really don't want your building to move, right? You want your building to be in equilibrium, and you're going to use these ideas all the time. So I really emphasize them. And of course you draw free body diagrams, but here's the thing. Don't forget free body diagrams. You draw a free body diagram to figure out what your torque is as well as your net force. Yes?
So if we were trying to find the angular acceleration, we can solve for the torque because we know what all the torques are.
Right.
And then I don't remember how to solve for I.
Okay. If you have an object that's a uniform stick, you might be able to use one of the equations. They usually provide them for you, or they're gonna expect you to be able to calculate it. Just to review I really quick, because I don't have much time. Remember, I is equal to, well, what's the horrible equation for it? R squared dm. Now, if you say, oh gosh, how am I going to remember that? Well, think about this. If you have a little chunk of mass, and what is R? R is the distance from our axis of rotation. If you're really far from the axis of rotation, it is really difficult to angularly accelerate that mass. You know, if I put a little chunk of mass at the end of a really long stick, and here's my axis of rotation, and you want to whip this thing, you know, whip it good, back and forth, okay? Well, if you make this stick really long, it's hard to do that, isn't it? I mean, it's like picking up a shovel at the very end of the handle with a big, you know, a lot of dirt on the end of it, and trying to angularly accelerate it. That's a lot of torque you got to work against. That's a lot of rotational inertia. So just think, well, the mass matters, but how far away it is from your axis of rotation matters a lot more. So it's squared. Okay, so it's, right? It matters a lot more, so you got to square it. I mean, if you're, hey, little mental tricks like that help you remember stuff. And don't forget the parallel axis theorem. I equals ICM around the center of mass. The I around the center of mass plus md squared. They might give you a situation where, you know, they'll give you the rotational inertia about the center of mass, but the axis of rotation is offset from it. And so this is your offset. This is how far your axis of rotation is from that. Okay, so this is what I like to do in review sessions, is I just give you a quick little primer on one, maybe two major ideas to try to jog your memory. Also, what's really nice about this, and I think this is very powerful for those of you going to college, and you're going to be studying this stuff again, is that what we're going to be doing, what we've been doing all year, is we've been looking at each little bit and piece. Okay, we're going to do this little chunk and this little chunk and this little chunk of mechanics, and now we're doing the same thing in E&M. But now when we're doing the review session, we're trying to put it all together. And we're trying to trying to see the big picture. And I'm telling you, that's when physics becomes really satisfying. I mean, that's when physics, you go, wow, the universe is just put together in this way that just makes, now you have to study it, and it doesn't make sense at first, especially E&M. But it really, we really have figured out at, the macroscopic level, the level of everyday stuff, we really have figured it all out and how to make it all work. And this is why we can, make robots and have flushable toilets and all the rest of the lovely aspects of our civilization, air conditioning and, document cameras and stuff like that. Okay, so that's it.